In this first semester, usually I'm teaching the finite element analysis of structure, so which is a application of principle of virtual work. Okay, so today I like to introduce the finite element method a little bit, and from next year, so actually in each year I teach the structure class in spring semester and FEM class for fall semester, but next year I don't want to teach the structure class because there are few students. So next spring I'm going to teach the fluid structure interaction, and next year I'm going to teach the structure. So I'm going to teach this class every 2 years. Okay, so most of you already know the name, the finite element method, and then some of you already can use the commercial software based on finite element method. So today's topic is introduction, just introduction. Introduction to finite element method. This finite element method was a very hot topic 20 years ago. But now it's very well developed and become classic. Okay, so you should remember this is a really nice application and maybe most successful application or principle of virtual work. So, in many cases, we have a physical problem. We want to solve some physical problem. So, we want to solve some bending moment, maximum bending moment of some ship or floating structure or offshore structure. So we want to calculate we want to design some large structure, right? So that would be your physical problem, engineering problem. So to design that kind of structure, first of all, we need to analyze, right? So physical problem is given, and to analyze some physical problem. So how can we do that? We need to solve some mathematical model, right? So mathematical model. But mathematical model can capture only governing phenomena. So from this stage and to this stage, we need to use assumption. So assumption means we idealize the physical problem. Okay? So the behavior of real physical problem depends on a lot of parameters, right? But we cannot consider all the parameters. So we only consider governing parameter. Very important parameter which affect the physical behavior. So usually mathematical model have a shape of partial differential equation, right? It has a shape of PDE, right? We are saying this is a strong form. So for solid mechanics problem, we derive the many partial differential equation, right? Local equilibrium equation is a partial differential equation, right? Strain displacement relation, this is also partial differential equation. Boundary condition, which are also part of partial differential. So to solve some physical problem, first of all, we need to make a mathematical model which can represent the governing behavior, and it can be written by partial differential equation, and we are saying this is a strong form, right? There are solution methods, two solution methods. We can directly solve that strong form. You remember? Displacement method and force method, stress method. That's a direct solution method. So we can solve this strong form. Solve direct solution method. Then approximation. Approximation method. So the direct solution method means we solve the partial differential equation in strong form directly. But you already know how to solve, right? So that direct solution method can be used for only simple problem, just spark case and one-dimensional case, simple two-dimensional case. But really, really general case, like engineering structural case, we cannot use the direct solution method. Okay? So this approximation method is very important. So direct solution method deal with PDE directly, and here we are using weak form. Based on principle of virtual work in solid and structural mechanics. Okay. So today I'd like to derive the finite element formulation from the principle of virtual work. Okay, so let's rewrite the principle of virtual work. Principle of virtual work, okay, internal virtual work equal external virtual work. Plus UIDS. This is the principle of virtual work. For linear elastic case, we can rewrite this equation by using material law. So and right hand side is the same. So we use the material law here. The C is a material law, right? Post tensor. So here I wrote the principal virtual work with tensor form. So stress is a 3 by 3 matrix. Strain is a 3 by 3 matrix. And force are vector, which has a 3 component. And this displacement is also vector, which has a 3 component, depending on displacement in x, y, z direction. Right? Now I like to write down that principal virtual work in vector and matrix form. So I like to define the stress vector. Actually, stress is a tensor, 3 by 3, second order tensor, but we can write down this stress with a vector. So 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 3, 1, right? Stress has a 6 dependent component, right? Because stress tensor is a symmetry. Also, strain we can define the strain vector. This is vector. Strain 1, 1, 2, 2, 3, 3, gamma 1, 2, gamma 2, 3, gamma 3, 1. Here gamma ij is an engineering shear strain multiplied by 2 Eij. Okay, engineering shear. Shear strain. Then we can write down the material law. So stress vector equal C strain. This is material law. So C become matrix, right? So by using the stress vector and strain vector and material matrix, material law matrix, I can rewrite the principal virtual work here. So I'm going to write on the top. Then you can compare the equation very easily. Let's look at this equation. Okay, left hand side. This equation become same integration, but instead of strain tensor, we can use strain vector, just vector, transpose C, okay, and something like this. And also, this is the same to this, same, no difference. Okay? d omega equal U transpose F d omega plus U transpose T D T S. So here we should use transpose. So let's look at this form. Fi Ui, this equal F1 U1 plus F2 U2 plus F3 U3. What's this? This dot product, right? So to make dot product with a vector operation, we need to use a transpose. Okay? You already know, right? Okay, so this is the same principle virtual walk, but little bit different form. John, I like the SQ. So I like SQ the result of this term. Okay, result of this term. Is that scalar, vector, or matrix? If you calculate this term, what kind of value you have, right? Okay. Vector. It gave us scalar, vector, matrix. Which one? Matrix? Matrix? You think so? So you think this term will give us matrix, right? Really? So is there anyone who has a different idea? So what's the meaning of this? This is internal virtual walk. Okay? So you can think the walk can be represented by matrix. Walk is just one value, right? So result of this scalar. Scalar. Dot product. It gives us one value. Okay? This is also dot product, one value. This sum two. Matrix, vector. So for example, here we have a matrix. So something like this. This will give us just one value. Let's say C. Okay? Okay. So now I'd like to introduce very important concept, finite element discretization. Let's think about the domain we want to solve here. So first, I like to discretize this domain with a small part of area, something like this. Okay? So we can discretize with a many sub-area, right? So here I subdivide the whole domain with a rectangular. Actually, so we are saying each subdomain is an element. Actually, finite element. Okay. And this element is defined by node. This is node. This is node. And so this is node. So you can think like this. We divide the whole domain with the many subparts, and which is named element. And element defined by node. Right? So, for example, this element defined by this 4 node in this case. So let's say this is element M, and this is node I. So we have many elements here. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 elements and many nodes, right? So here you should understand the concept of node and element. Okay? It's not a difficult concept. So if we sum all the domain of this element M has a domain M, volume M is become total domain. So if you sum all this area, you can have the total approximated area, right? Okay, and now it's node. Node I have, let's say, has nodal displacement. Nodal displacement UI, VI, WI. So we define the nodal displacement. So we define the displacement and node here. Okay, node I is here. So this is UI, VI, WI, something like this. We are saying this is nodal displacement, nodal. So nodal displacement is the displacement at node. Okay? Displacement at node is a nodal displacement. So today I introduce some important concept. First, element. Second, node. Third, nodal displacement. Okay? So for general 3D solid case, we have a 3 nodal displacement in x direction, y direction, z direction. So let's define one more nodal displacement vector. vector. So nodal displacement vector is u. This is vector. It consists of all nodal displacement. So u1, v1, w1, okay, u2, v2, w2, and something like that. Nodal displacement vector contain all the nodal displacement. So nodal displacements at element I contain only 3 components, but nodal displacement vector contain all the nodal displacement components. So at each node we have 3. So if we have 10 nodes, and then we have a 13 member of nodal component in the nodal displacement vector. Okay, now interpolation. We interpolate the displacement. This is a displacement of element M. So let's say this is the element M. It has a 4 node here. So here, displacement at this point, displacement is like this. This is a U, M. This is element M. So this is a displacement field inside of the element. Okay? So this displacement field is defined in element M. Okay? Not defined in other elements. This displacement of element M can be represented by, approximated by some matrix H and nodal displacement vector U. So here we say M equal displacement field. Of element M, H is a displacement interpolation matrix. Matrix of element M. Okay. In this stage, I don't want to show you how to make that displacement interpolation matrix. And by some example, I'm going to show you how to build that H matrix. Okay? So if you look at that equation, we can find out displacement field of element M, okay, can be interpolated by nodal displacement, okay, displacement at node. So displacement field is directly linked to the nodal displacement. Okay, and this nodal displacement is shared by the other element here. This element and this element, both elements share same node. They're sharing, right? So field of this element is defined by approximate this 4 node. Displacement field of this element is defined by this 4 node. So through the intersection, displacement is continuous, right? Okay, so similarly, we can interpolate virtual displacement with the same interpolation technique, HM, U. This is the virtual displacement field of element M. This is virtual nodal displacement. Virtual displacement field of element M. So here very important thing is that we use the same interpolation for virtual, real and virtual displacement. So we are using the same interpolation, right? You remember the example I showed you in the last class. In that class also, we use the same displacement pattern for virtual and real displacement, right? This is very important to result in the symmetric stiffness matrix. If we do not use the same displacement field, we cannot have a symmetric property. Okay, so now we know how to approximate the displacement, right? And we know the strain matrix. Strain displacement relation for small strain Ui xj plus uj xi. Using the relation between strain and displacement, we can calculate the strain. From the nodal displacement, U, and also virtual strain from the nodal displacement, virtual nodal displacement, U. Because we already know the displacement, if we put this into this equation, we can calculate here the B matrix. Okay, so B matrix gives us the relation between strain field of element M and nodal displacement. Okay, so this matrix B relate the U and strain, nodal displacement strain. H relate the displacement and nodal displacement. So B and H is a little bit different. Okay. Then let's write down the principal virtual work again. So T C equal Tf d omega plus ds. So using the relation we obtained from the approximation, we can write down this equation like this, m. Because we subdivided the old domain with the element sum m, strain m, c m, we can change the principal virtual work for finite element formulation. Okay, let's look at this equation here. Here, instead of a virtual strain, I put the virtual strain for element M, right? C is a material matrix for element M. This is strain for element M. So from here to here, this is the internal virtual work. Internal virtual work by element M, right? And really important thing is that here we sum. If I sum all the internal virtual work done by element M, we can calculate the total internal virtual work. So we have a sum here. Okay? And for also external virtual work, we have a sum here. So this virtual work done by external body force, it can be calculated like this. This is a virtual work calculated by surface. So here I put the S. This means displacement on surface. So we need to sum all the surface. So, for example, in this finite element model, this is surface. This is surface. This is surface. Okay? Outside. This is surface. To calculate this term, we need to calculate the surface. Surface also defined by node, right? External node. Node position on the surface of finite element model. Okay, now let's modify this equation again. Using the relation here. Let's use this relation. Let's use both equations here. Then we can have transpose B U. This become internal virtual work. So here I just put these two equations in this equation, right? And nodal displacement, virtual nodal displacement and real nodal displacement is just constant. So it can be outside of the integration, right? It's not change in the element, right? So it can be outside, something like this. And similarly, right-hand side also become U transpose H M transpose F M D omega M plus U. Sorry, we don't have U here. Right? So here we have H. H here HS here. Little bit different. HS is calculated from H. So HS is a interpolation function on surface, only on surface. Okay? So you know how to calculate this equation from here, right? So still, here left-hand side give us scalar value, right? It's internal, total internal virtual. Right-hand side also give us one value, right? We should remember. And now the next procedure is also quite important. In that equation, let's apply U vector. Okay, let's apply apply U transpose equal 1, 0, 0. Now all the 0. Let's apply some special virtual displacement pattern which has only have a unit value for the first nodal displacement component and others 0. Okay? If I apply this equation to here, we are going to have one linear equation. Right? And next, let's apply second term component 0 is 1 and others 0. So we are applying the virtual nodal displacement pattern sequentially like this. So if apply so something like this. So whenever we apply the virtual displacement pattern, we can have one linear equation. First linear equation, second linear equation, third linear equation, fourth. So finally, we have n linear equation, right? The number of n is equal to the number of nodal displacement component. Okay? So we can have an n by n metric system finally. So that procedure can be simply introduced by, in this form, deleting this virtual displacement here. Okay? Same procedure. If we delete both, we can have one. Then, finally, we have a metric system Ku equal R and K equal sum of K M. This is stiffness matrix, and K M equal M B T M C M B M D omega M. So let's look at the K here. K is a stiffness matrix of a total system, and Km is a stiffness matrix of element M. So if we sum stiffness contribution of each element M to the total stiffness, we can have a total stiffness. So also R. Here R is defined. R is a load vector. Here K is a stiffness matrix. R is a load vector. R equal sum M R M, and R M equal H T M F M D omega M plus ds. Okay, so R is a total load vector. Load vector for the whole system, and which can be calculated by summing up the load vector of each element. Load vector, load applied to each element. Okay, so this summing procedure, we are saying this is assembling procedure. This assembling procedure is a very effective procedure. When we calculate stiffness matrix, we just consider first each element and then just summing. Then we can calculate the total stiffness. This is a very useful and effective concept to model and to solve the very complicated system which has a very complicated geometry. So in the next class, I show you simple example. Then you can understand the finite element procedure more clearly. Okay? Any question?